This is section 11.9, representations of functions as power series. So we're going to be writing functions like this into a power series like this. And it turns out to be a geometric series where it's convergent when the absolute value of x is less than 1. So let's see if we can write this function in a series. So that's what the directions say. Find a power series representation for the function and determine the interval of convergence. So first things first, we need to make this look like that. So we can, let's do this. So we got 4 over 2x plus 3. We can rewrite that as 4, 3 plus 2x. I just reversed the two terms on the bottom. I'm going to factor out a 3. So I'm going to have 4 thirds, 1 on the top. If I factor out a 3, I'm going to have 1 minus negative 2 thirds x. So I factored out a 3 from the denominator, and that's how I got 1. If you factor out a 3 from this term, you get 2 thirds, and then I made this a double negative instead of a plus, so that it looks like that. So this becomes this. So now we can say that this power series will look like this. 4 thirds, and we're going to have the sigma as n from 0 to infinity of negative 2 thirds x to the nth power. We're just using this definition now, or this theorem. All right, now we can actually rewrite that. This is really 2 squared, and this is 2 to the nth, so that's going to be, and we can also take out the negative 1 to the nth power and write that separately. So this is going to look like this. Negative 1 to the nth. So I took care of this negative to the nth. The 2 to the nth plus the 2 over here is going to be, it's going to look like 2 to the n plus 2. And then the bottom, you have an additional 3 over here, so it's going to be 3 to the n plus 1. And then you still have the x to the nth power. So this is a power series representation of this function, and it converges when this is true. In this case, our x is this. So when the absolute value of negative 2 thirds x is less than 1, and that implies that well, the negative is going to disappear, and then you multiply by the reciprocal, so the absolute value of x is less than 3 over 2, and that's our radius of convergence. And our interval of convergence is going to just simply be, since it's centered at 0, negative 3 comma 3 halves, comma positive 3 halves. And for these, because we're using the geometric series instead of the ratio test, we don't have to check the endpoints. It's always going to be open parentheses for these. So we're done. All right, let's do the same thing for the next one. So let's rewrite this function as, you can write that as an x, you can write that as a 1 over 1 minus double negative once again, just like we did last time. All right, so now we have that x times the series n equals 0 to infinity. And this becomes what goes here. So that's going to become our negative 2x squared to the nth power. All right, and we could rewrite that as the series n equals 0 to infinity. You can take out the negative 1 to the nth again. And then you got 2 to the nth, and then you're going to have x to the 2n from here, but then you have the additional x, so you can add 1 to that to compensate for this additional x. And that's it. That's your power series representation of your function. This is equal to that function, and we know that it converges when this part, absolute value of this is less than 1. All right, the negative 1 will disappear because of the absolute value, so that just means that x squared less than 1/2, which also means when the absolute value of x is less than 1 over radical 2. All right, so that's going to be our radius of convergence, 1 over radical 2. And our interval of convergence is going to be negative 1 over radical 2, positive 1 over radical 2. And that concludes that. All right, let's take a look at the next theorem. All right, it says that if the power series has a radius of convergence r greater than 0, then you can, there's your power series. It's differentiable and therefore continuous on this interval. So the derivative is going to be the derivative of the series. So in other words, the derivative of the function is equal to the derivative of the series. So that's what they're saying. And likewise, the integral of the function is going to be the integral of the power series as well. And the radii of convergence of the power series are both r. All right, so this one's going to be a little long, so bear with me for this problem. So the way they kind of start us off is they give us this function, and you're kind of supposed to anticipate what the original function would be, so that when you take a derivative, you eventually get this. So you kind of have to have a little bit of intuitive sense here to know that you should probably start with this function, 1 over 2 minus x, which can be written as 1 over 2, 1 minus x over 2. And now we can write that as a power series. The 1/2 comes out, n equals 0 to infinity, and then we have x over 2 to the n power. So this is kind of what we were just doing using this. So nothing different here. All right, and now we are going to say that this can be written as the series of 1 over 2 to the n plus 1, x to the n. So we just separated, the x to the n is here, the 2 to the n plus the additional 2 became 2 to the n plus 1. All right, so now we can write, well, the derivative, based on the theorem above, of the original function that we began with is equal to the derivative of the power series that we just found. All right, so that's going to be the derivative of the series that we just came up with, which is going to say that, let's write that down here, the derivative of, so this derivative here, you can verify that it's going to be 1 over 2 minus x squared. I'll let you verify that. And then the derivative of this, well, that's just the power rule. You bring down the n and then you subtract 1. So that's not too hard. It's just going to be 1 over, whoops, forgot the power series. The constant stays the same. That's not affected, but then you have the n, and then xn minus 1. That's the derivative of this right here. So I just brought down the n, and then subtracted 1, and the constant just stays the same. All right, so we did that. That's the first derivative. So as you can see, we're getting closer to the third power, which is what we need. So we got to take the derivative yet again, so we're going to do that. So I'll just write, and the derivative of this now is going to equal to the derivative of the power series yet again, the series that we just differentiated. All right, so that's going to look like this. If you take the derivative of this here, you can verify that it is indeed 2 over 2 minus x to the third power. And now we have that third power that we needed because we needed to work our way up to this. So we're getting closer and closer. Whoops. And that is going to equal to the power series of, and actually this is a little tricky here. It's a minor thing, but if you plug in 0 for n, it's going to be 0. So what they do is they just change this index to be 1 instead of 0, because that 0 term doesn't do anything. All right, so that's what they do here. And over here, they're going to do the same thing, but now it's going to be 2 because it's the second derivative. And you will see what happens. When you take the derivative of this, you're going to bring the exponent down. So it's going to be n times n minus 1 x to the n minus 2. All right, that's the derivative. But when you plug in 2, I'm sorry, this was 0. But when you plug in 0, that goes away. If you plug in 1, that disappears. So that's why they started at 2. Because the 0 makes everything cancel, the 1 makes everything cancel, and so now they begin at 2. All right, so you need to make this back to 0. So what you do is you make n equal to n plus 2. That way when you subtract 2, you get 0. So if you replace all the n's with n plus 2's, that's going to change this to 0. So this is going to be equal to the series of n equal to 0 to infinity of 1 over. So remember, we're replacing n with n plus 2. And so this becomes n plus 2 plus 1 is n plus 3. All right, this n becomes n plus 2. This n is n plus 2 minus 1 is n plus 1. And then you have x to the n plus 2 minus 2 is just n. And there you have it. All right, so that is the power series representation of this function. But we're still not done. So thus, we can say that the function that is originally given to us, which is this one, is the same thing as x to the cube, 2 minus x to the third power, equals x to the third over 2 times 2. So you just have to get a little creative by the way you represent this, because we want to use this. So there it is. But you want to cancel the 2's out, so you have to put a 2 down below. And you still have the x cubed that you need, so there's your x cubed. So we're just being creative in the way that we write this, so that we can use this function, and therefore we can use a power series representation of it. Okay, so now, finally, we can use this representation here, substitute this into that, and we're going to have x to the third over 2, n equals 0, n plus 2, n plus 1, all over 2 to the n plus 3, x to the n. So all I did was I brought this and I replaced that with this. And here's the x cubed over 2 part. And so this can finally be written as, all I got to do is add 1 to this. This 2 is going to add 1 to here, so this is going to be a 4. And then this 3 will be added to this, so that's going to be n plus 3. So I'm just going to erase this. And this is going to be n plus 3. And this is going to be 2 to the n plus 4. And that is it right there. That is the answer. And our radius of convergence, because x minus 2 over 1 must be x over 2 absolute value, because of this part, that's how it's going to be when it'll be convergent. Converges when that's true. That implies that the absolute value of x is going to be less than 2 when you multiply the equation by 2, or the inequality by 2, which tells us that the radius of convergence is 2, and the interval of convergence is going to, oh, actually, that's not what they're asking for. They're just asking for radius of convergence in this case. So we are done there. So they're just asking for the radius of convergence. And that is it. All right, that was a hard problem. Let's move on to our final problem. Now we're going to do the same sort of thing, but now this is going to involve integrals instead of derivatives. So here it is. Evaluate the integral as a power series. So we don't want to evaluate it in the integral form. We want to convert it to a power series and then integrate that way. That's the whole idea. So let's just focus on the integrand. And we can rewrite that as t over 1 plus t cubed is equal to t times 1 over 1 minus negative t cubed. And that means that the power series is going to look like this. All right, and we can add 1. Well, let's separate the negative 1 first. All right, and then the t to the 3n plus 1. So that's going to be t to the 3n plus 1. All right, so that means that our integral that we are given can be written as c plus, that's a constant of integration. Instead of integrating this, we're going to integrate this series. So the series, if you integrate it, all you got to do is add 1 to the exponent and then divide by that new exponent. That's how we do that. So this is going to be the constant doesn't change. So the exponent, like we said, we add 1 to it. So it's going to be 3n plus 2. And then we divide by 3n plus 2. All right, so that is pretty much it. So we evaluated the integral, but we used power series instead of our techniques of integration. So this is it right here. All right, and we know that it converges when this part is absolute value of that is less than 1, which means that when t is less than 1, absolute value of t. And so that means that our radius of convergence is 1. All right, so that is pretty much it. So because of the radius of convergence of this series is 1, that means that the radius of convergence of the integral is also 1. That's what the theorem says. And that pretty much does it for this problem.